Hello, everyone. Welcome to our Sentinel Motion webinar today. My name is Wyatt Pena. I'm a project manager here at Ridgetop Group. And today's webinar on Sentinel Motion will be presented by myself and our soon-to-be PhD in mechanical engineering, Mohsen Azimi. So, given it is just a minute after 10 o'clock, we'll go ahead and get started today. For reference, we'll be asking everyone to hold questions until the end. And if we get a lot of questions towards the end, feel free to use the chat box feature here in the GoToMeeting tool. For today, our agenda will be giving an introduction into Sentinel Motion. We'll cover the RotoSense development history, some ongoing research and vibration analysis of gearbox systems, which is the work that Mohsen has been working on. And also, we'll cover some applications for Sentinel Motion in the railroad industry, as well as general applications with the RotoSense development kit. At the end, we'll summarize and have some time for questions. So if we recall, for those of us that have been participating in this PHM webinar series that Hafi started over the last couple of months here, we've been focusing a lot on these different types of frameworks in a PHM and CBM system. So today we're going to be focusing on the control and data flow framework as implemented in Sentinel Motion. So Sentinel Motion is a family member of the Sentinel Suite family of products, and we'll be taking a kind of a deep dive into how the different types of sensor framework with RotoSense, some of the feature vector framework with the edge computing, all interact in this kind of modular system that we have going on. So just as a reminder, we'll be having additional webinars monthly. The next webinar will be on Sentinel Power. This slide right here gives us an overview on what Sentinel Suite is. So Sentinel Suite is a family of advanced sensing, monitoring, and diagnostic solutions for complex systems. These solutions are based on Ridgetop Group's condition-based maintenance and prognostic health monitoring system architecture and comprise sensors, anomaly detection, prognostic reasoners, and graphical visualization tools. Sentinel Motion will be our focus today, and with this particular family member, we monitor electromechanical systems of aircraft, infrastructure, wind turbines, and other equipment to prevent unexpected downtime. Sentinel Power is utilized to analyze and diagnose power systems through prognostic-enabled smart sensors such as SmartProbe. Sentinel Interconnect is used to monitor intermittencies or failures in interconnects at both cable level and also the solder joint level. Sentinel IT is used to monitor IT networks and backup power supply systems to kind of analyze the health of different computer systems. So if we look at where Sentinel Suite fits in a CBM/PHM ecosystem, this is very much related to the different types of framework that Hafi laid out in previous webinars. At the very beginning of this particular system, you need a way to communicate that data, right? So that's that sensor framework. And then you have the Sentinel Suite family members that does the control and data flow framework, which can then interact with different types of algorithms and reasoners to produce a real-time state of health and remaining useful life. So what happens after those estimates are obtained for different applications is very much application dependent. So turning this type of prognostic data or CBM data into meaningful action items is up to the customer, and we work very closely with them to make sure that we're doing the right types of action items for the given application. So what is Sentinel Motion? Sentinel Motion is an IoT-based sensor system that monitors mission-critical equipment by observing any combination of temperature and linear, rotary, or vibrational force. Sentinel Motion comprises a wireless network of RotoSense smart sensors and the Sentinel Gateway communications device. The Sentinel MotionView software package is also a part of this system, and that is what's utilized for data acquisition, analysis, and sensor-to-gateway management. Sentinel Motion is able to extract high-resolution acceleration signatures caused by gear faults, stresses, and/or faults in hardware and machinery in a wide number of applications. So on the right here, we have our standard RotoSense form factors. The RotoSense Series 1000 was the first particular form factor that was developed with NASA, and we'll cover a little bit of that development history in today's presentation. So what is a Sentinel Gateway? Sentinel Gateway is a solution for the RotoSense data acquisition and the network management. Sentinel Gateway is the primary communications device that brings edge computing to industrial applications in which RotoSense is deployed. When combined with the RotoSense smart sensors, the Sentinel Gateway provides an end user a complete data acquisition toolbox and has the following features and benefits. With edge computing, you're able to utilize near real-time data processing at the source of the application. This results in only key analytics that will be pushed to the cloud as opposed to all of the raw data. When you look at different types of applications and you have hundreds or thousands of sensors all trying to push different types of data to the cloud, in certain situations that's really not feasible or cost effective. So being able to bring edge computing and extracting key analytics of interest and only pushing those analytics to the cloud is a very useful benefit of this type of IoT architecture. The gateway also has a secure access point and a GPS module and hosts the Sentinel MotionView software application. So the Sentinel MotionView software application is a primary graphical user interface that interacts with the Sentinel Gateway and the RotoSense IoT network. The software application and acquired data can all be found on the secure network drive provided by the Sentinel Gateway. Sensor data can be integrated into other connected systems by downloading the TXT and CSV data files or by exporting them through an API. Sentinel MotionView is also offered as an iOS phone app on the App Store. So some deployment options for customers to consider for Sentinel Motion are kind of across the board. We've had customer interest and interactions in the railroad industry to monitor tracking and vehicle components, also helicopter transmissions and gearbox systems, CNC systems, downhole oil and gas, wind turbines, construction equipment, and also industrial equipment and heavy-duty equipment that can be found on construction sites or in the mining industry as well. So an online visual of the edge, we talked a little bit about the Sentinel Gateway having edge computing. This gives you a very good visual of where the sensor and IoT network kind of fits here, right? So this is very much related to the PHM and CVM system architecture that Hoffby outlined, where you have your sensor framework, your feature vector framework, and your control and data framework kind of all interacting with this control and data framework. So this is kind of provides validation for how we treat the IoT with the gateway and edge computing for a large number of different applications. So the RotoSense development and our NASA testing, we'll cover this next here. So RotoSense was originally developed with NASA as a wireless MEMS-based vibration sensor for gearbox fault detection. A key feature of this particular sensor design at the time is that the sensor was embedded in the component of interest, which was a helicopter gearbox system. By doing that, we were closer to the source of vibration and had direct measurement without losses in transmission of vibrational signatures that normally have to translate through bearings, chassis, and housings. So that's unlike traditional case-mounted accelerometers. RotoSense is also a low-power wireless communication device, which supports a large number of different sensors in different applications. Testing was performed at both Ridgetop and the NASA Glenn Research Center using the transmission of a Bell OH-58 Kiowa helicopter. So if we look at some of the testing that we did, you can see in the upper right, that's the RotoSense Series 1000 module and being embedded in that particular pinning gear system. And on the left, you can see where it's intertwined with that rotating shaft. So some conclusions from the NASA testing was that RotoSense performed as expected through 113 hours of testing at speeds of up to 6,000 RPM. The single RotoSense smart sensor obtained as much data as 5 case-mounted accelerometers without the added weight of additional cables. Further analysis of vibration data has revealed more as all 3 degrees of freedom in the plane of vibration have been captured simultaneously. This is the NASA spin-off article. These slides will be distributed for all registered attendees, so definitely if interested in finding out a little bit more about that particular experiment at that time, feel free to take a look at it. So now we'll be moving on to the next section where Mohsen will be talking about some of the ongoing research in vibrational analysis of gearbox systems.
Hello everyone, my name is Mohsen and I'm going to talk about the results that we got for vibration analysis of gearbox system by using the RotoSense. The next slide, please. First of all, I want to talk about the existence of the vibrational signal in gear system. Why do we get this signal in any type of geared system? The reason is simply shown on the right-hand side picture. As you can see, the contact point of the gear and pinion changed during the rotation. And this picture that you see, number 1, 2, 3, repeats for every contact, every time that pinion and gear come into contact. So this is why you can, the signal that is shown on the right-hand side exists in any gear system, no matter they are healthy or they are damaged. But the signal that you see here is for a healthy system because everything is smooth and is repeating in a harmonic way, and there is no abnormality in this signal. But this is the key, and this is the feature that is used to determine if there is any abnormality or fault in the system or not. Next slide, please. So if there is an abnormality in any of the tools that can be caused by pitting, spalling, peeling, or anything, so whenever these tools come into contact with either pinion or gear, it's a matter of which one is faulty. Then there is abnormality in the vibrational signal, as you can see on the lower picture here. So the problem is to determine if, is to measure this vibrational signal and determine if this abnormality exists in this signal or not. So this is simply the whole fault detection process of any gear system. Next slide, please. So far, the common method that everyone uses for this fault detection to collect this vibrational signal is to mount one accelerometer or even more on the bearings of the system, as you can see in the top picture, or on the gearbox, like the picture on the bottom. It's just a matter of the design of the system, but either way, this vibration signal is collected like this and then is analyzed to see if there is any abnormality in the signal or not. So after the signal is collected, there are 3 major methods that is commonly used to determine if the signal is faulty or not. The very early method is time domain analysis. This type of analysis can determine if there is anything in the signal or not, but it doesn't tell us what is the frequency of this abnormality. The problem with this is that we cannot determine where is the source of the signal that we are getting. For example, a system can have 10 components, 10 gears. Which one of these gears is faulty? If we have information of the frequency, then we can determine that picture. And the same thing is for the frequency domain analysis. If we apply this method, then we don't have any information on the time. Sometimes the vibrational signal is recorded for a long period of time, like 1 week. But when this bad phenomena happened, it was like the first day or second day or the last day. This is why the time frequency domain analysis is very common, and these days everyone uses either window Fourier transform or continuous Wavelet transform. But in this work, we focus on the window Fourier transform, and in the next slide, I'll tell you why we chose window Fourier transform. Next slide, please. On the top of this slide, you can see a plot of the signal and related FFT of that signal. And on the bottom, you see the wavelet that is the signal used for both window Fourier transform and wavelet transform. So this wavelet is actually the window that we want to look at the signal through that window and just analyze that part of the signal. So practically, this wavelet will be multiplied by the signal, and the part that the wavelet is 0, the signal will go 0 and is not considered, and just the part that is non-zero will be studied. And this wavelet should shift through time, so we can analyze different parts of the signal at different time zones. The difference between window Fourier transform and wavelet transform is that in wavelet transform, the size of this window varies for different frequencies to get a better resolution. But in window Fourier transform, the size of this window is constant. But in this work, since we are focusing only on the local faults on the gears, and we are not concerned about the harmonics of the system, so we are using the window Fourier transform because all these local faults, they appear as a signal with 0 frequency. So this is why we use these tools in this work. So far what I explained was the common method for collecting the data, common method to analyze the data. But before I start talking about what we have done, I go through the deformation and vibration in continuous system, just a very short classification that what type of vibration do we have in continuous system. Based, as you can see, there are 3 groups here, 3 pictures. Based on the direction of the force applied on the system, we can have longitudinal, transversal, and torsional vibration. And it's just a matter of the direction of the force, not the shape of the part or the form of the cross section. But there is a difference for each one of these cases. There is a best location for collecting the data, and that is the important part that I am providing this slide here. For example, for longitudinal, every location on the cross section of the shaft is a good candidate to mount the accelerometer and collect a vibrational signal. But when it comes to the transversal vibration, only the top part and the bottom part of the shaft are the best part for this, and this is because these points, they have the most deformation. So it's the largest deformation is happening on the top and on the bottom. This is why for the longitudinal, all the points on the cross section, they have the same deformation. So this is why all points are good. And when it comes to the torsional vibration, any points on the perimeter of the shaft is a good candidate for this, since they all have the maximum deformation. So the next thing that we need to consider is that which one of these vibrations are happening in the system, in the gear system, and we mount the accelerometer on the right place and in the right direction to collect this vibrational signal. Next slide, please. It's a very simple schematic of a gear system. Everyone knows that there are more than one bearing there, but it's just for the simplicity. We just have one bearing. There might be several transmissions. We are just keeping it as one transmission, one pinion, one gear, and the load, as you can see on the left. So the red force is the force applied from the pinion to the gear, and it's the driving force. Then, because of that force and using Newton's law, we know that there is another force, a reaction force, that's coming from the bearing to the shaft to support the system, which is shown by green. The red force creates a torque because it's not applied on the center of the shaft. This overcome the applied load and keep the system running. So existence of the applied load and the reaction force are both as a function of this applied force that is shown by the red. But before we talk that, this red force is fluctuating because of the fact that the contact point is moving. Therefore, if the applied force is fluctuating, so the reaction force and the applied load will be fluctuating too. But this fluctuated force applied from the, first we'll focus on the bearing, the green force applied from the bearing to the shaft. So so we prove that this force is fluctuating. Now, this force is coming from the bearing to the shaft, and when this force changes, therefore when there is this force on the bearing, then there is deformation on the bearing as well. And this is why most of the studies that you have seen, they mount the accelerometer on top of the bearing, because this accelerometer is actually measuring the deformation of the bearing because of this screen force. But the fact is that this signal, this force, must go through all layers of a bearing. It goes through the inner race, roller, outer race, and case, and finally get to the accelerometer and be recorded. So going through all these layers cause that we lose some part of the signal, and some part of it will be down. I would say this is one bad feature about measuring the signal in this way. So this is why we are mounting the accelerometer on the shaft with RotoSense, as you can see with the blue accelerometer on the left. So to mount this accelerometer directly on the shaft, so we can measure either the transversal or torsional vibration of this shaft directly from the shaft. And as you can see here, there is no force on the longitudinal direction. So there is no longitudinal deformation or signal, vibration signal. Therefore, we have two types of continuous vibration here that we want to study. Next slide, please. So this is the test bed that we designed and we set up for this experiment. On the right-hand side, you see the DC motor in blue. On the left-hand side, you see the motorcycle brake that we use as load. There is one stage per gear transmission on the middle, and the red disc is where we are mounting the RotoSense. Next slide, please. Three different gears with three different locations for the faults are used for this test. So each direction that we mount the accelerometer, we use these three different cases to make sure that we are measuring the right signal and we are locating the location of this fault correctly. Next slide, please. So we have 3 cases of fault. Then we have 9 cases that we are in each case that we mount the accelerometer in a specific location and we measure the accelerometer in a specific direction. The first column is related all to the longitudinal vibration that, as we know from the theoretical part, there should not be any good signal there. But anyway, I'm doing this just to compare and make sure that everything is correct. The middle column is for the transversal vibration that we are placing the accelerometer on different locations. As I talked about this, on the center, there is no deformation, so we don't expect to get anything good on the center of the shaft. But anyhow, we are doing it on the center, on the middle, and on the perimeter of the shaft to see how things change. And the same thing for the torsional. As you see, the location of the accelerometer in each row is the same, but the direction that the acceleration is recorded is different. So after, I'm not providing all the data that I collected for all these 9 cases multiplied by 3 different faults that we have, but the result was that we didn't have a good data from the longitudinal, and we had the best result for the transversal and torsional for each one of them when the accelerometer is mounted on the perimeter as we expected from the theoretical analysis. Next slide, please. In the next slide, I want to compare these 2 best that we got. So the best for the transversal and the best for the torsional vibration is provided here. As you can see, for the torsional vibration, we got a better vibration signal. We can see all the harmonics up and down, but the transversal vibration, the signal is more flat and there are less information here. But anyway, this transversal is actually what has been measured on the bearing so far, and all the fault diagnostic have been based on this. So it's not like there is no information in this signal, it's just that torsional one has a better and a stronger signal. Next slide, please. So the torsional signal shown in the previous slide went through the window Fourier transform, and as you can see here, not that we determine that if gear is faulty, we also determine where is the location of that fault on the gear for 3 different cases that we have. Next slide, please. But so far we mounted the accelerometer only on the shaft. So the next step that is something left to do is to mount the same accelerometer, the same RotoSense that I used for the signal analysis of the shaft. Now we mount it on the bearing and we compare the signal captured here with the other 2 signals that we had that we collected from the shaft. But definitely, theoretically, we can say here that this signal should be less strong than the transversal signal that we collected on the shaft due to the fact that the signal collected here went through all the inner and outer rays and the rollers, and definitely it should be less strong. Next slide. So to sum it up, I can say that there are 2 main advantages for using RotoSense for fault diagnostic. The first one is that a lot of time we are dealing with a system that is very complex, and the bearings and the gears and the gearbox, they're all buried inside the system. So if you want to access that and mount the accelerometer and record the data, we have to dismantle everything. But if we use the accelerometer, we can just simply mount it on the shaft coming out of that system and just check if everything is working well or not. So it's very good for complex system that the gears are buried inside the system. And secondly, it can provide us a more enriched signal, as I showed it before, since we are measuring the signal directly from the shaft, not from the other component like the bearing that has less stronger signal. Thank you, Wad. I'm here.
Yep. Alrighty, so yeah, thank you, Mohsen, for showing us a little bit about that research. And again, those types of analytics and research are kind of what make future benefits possible, so the gearbox analysis and isolating faults and being able to characterize those are all part of the process. And with the IoT infrastructure that we have in place, we'll be able to embed these types of analytics on the gateway or the sensor itself and be able to look at particular features of interest. So it's all great stuff going on here. So this next section of the presentation, we'll be talking about Sentinel Motion for railroad applications. And this is a major area of focus that we've been working on here at Ridgetop Group. So if we put things kind of in perspective, the original testing with NASA and that particular development was done for kind of that gearbox analysis. And then we figured that it could also be applied to the railroad industry. And in 2015, we went to Pueblo Test Track in Colorado and was able to test that particular sensor revision and got some really good results. So we'll cover a little bit about that right now. So why did we go after this particular application area, right? So there's several different problems in the railroad industry. A list of the most common railroad problems are mechanical failures, railroad vehicles or components, and poor ride quality, which both kind of contribute to derailments down the line when these types of failures accumulate. Some of the common root causes of these problems that can be detected or monitored with RotoSense are broken rails/welds, failed bearings, defective wheels, unusual track interaction, and our aging infrastructure. So some of the other root causes are operator error, and that's actually the #1 root cause for a lot of derailments and different types of mechanical failures. So operator error, where excessive speeds, overworked crew, you got a tired operator, mistakes happen. But there's also root causes that allude to poor maintenance of the track geometry, and then also extreme weather conditions such as floods, heavy snow, etc. So some of the industry standards out there in the railroad industry to detect different types of failed components the most common are kind of wayside detection equipment such as hotbox detectors, HVDs, and wheel impact load detectors, which are wild systems. But they also conduct visual inspections, which is, you can see here on the right, there is an actual crew that'll go out and inspect different parts of the railroad. And after that, you have to accumulate or document your written reports and then issue a work order request. Another common practice is interval-based maintenance, where you replace equipment or components based on a number of hours or mileage. And then also there's reactive maintenance, so when things actually do fail or degrade, that causes an unscheduled breakdown, and that's very costly in the railroad industry. There's also automated track inspection vehicles, which are typically very expensive, and they vary across the board in terms of their sensing capabilities. Some of the emerging technologies are some of the big data analytics, forecasting, and advanced modeling, but those are both made possible through automated track inspection vehicles or IoT sensing devices such as RotoSense for voltage, current, shock, vibration, etc. Some of the application-specific track inspection vehicles and sensing tools also are emerging with new capabilities. So we're working with industry partners to kind of deploy RotoSense in this actual operating environment for the Class 1 operators. One comment I do want to bring up here is that interval-based maintenance and reactive maintenance are kind of the enemy of the problems that we're trying to solve here at Ridgetop. So a lot of our tools and solutions are based on condition-based maintenance and interval-based, or condition-based maintenance and prognostic health management. So on that note, we're able to, or the goal or the focus is to go away from reactive maintenance or even interval-based maintenance, so that you're replacing components or monitoring your systems based on actual data and physical degradation. So our testing at TTCI in 2015, which is the Transportation Technology Center that I was talking about in Pueblo, Colorado, was done on the high tonnage loop there. So you can see here on the right, RotoSense was mounted on an actual wheel hub of a tin can bearing system, and we were there for several days collecting a ton of different data. So you can see that same architecture that was in that cylindrical form factor or same component circuitry was kind of just adapted to this other type of printed circuit board layout and utilize all the same kind of sensing components. The aim of the testing was to detect track anomalies and correlate those to a GPS location, and then also detect any faults in the wheels, hubs, and bearing systems. So the test track legend and GPS correlation is shown here. As I previously mentioned, we went over that track several hundred times each day we were there, and by doing that, we were able to, along with the GPS, we were able to bin the different types of data features and detect things like different types of bridges, steel, concrete bridges, different types of railroad ties, different types of welds, and they all had a unique signature by mounting RotoSense in that particular mounting location on the tin can bearing system. So here are some of those testing photos. This is a very early revision of the gateway, much different now, but here you can also see RotoSense going over a particular type of weld. So, and then also this is the locomotive in which it was installed on. So some of the key testing results at TTCI is that we proved RotoSense is a viable IoT solution that could help categorize the railroad infrastructure and detect known and unknown track anomalies. We were able to detect different types of turnouts with and without frogs, welds of various kinds, concrete and steel bridges, crib ties, and others. So this validated that the sensor could operate in this harsh operating environment. 2015, when we went to TTCI, we were told by the installation techs that additional or other companies have tried to do similar sensing at that location, and typically they die. Those sensors, it's a very harsh operating environment. We spent a lot of time kind of hardening the design to be able to function there. So when you look at some of the IEC specifications for this infrastructure, they have a Category 1, which is, I think, a vehicle mounted, Category 2, which is bogie mounted, and then Category 3, which is kind of where the wheel mounted version is. So each of those have very specific vibration requirements or testing requirements, and we're able to operate in that harsh operating environment. So looking ahead, as I previously mentioned, Ridgetop Group is currently working with industry partners to deliver a complete solution to the Class 1 operators here in the U.S., and we're also working with different companies around the globe to help utilize this IoT solution. So the primary application areas are focused on monitoring bearing failures and wheel failures, and also detecting those track anomalies. So again, one of the things about the track inspection vehicles is They typically don't go over the track as frequent as the regular trains that are operating on them, but with RotoSense, you're able to actually go over it with more frequency. And if you do detect a track anomaly, we're not necessarily trying to replace the track inspection vehicles, but now that you know a particular location, you can send over your track inspection vehicle to get higher fidelity measurements. So they kind of complement each other quite a bit. Also, with hot box detectors and wild systems, those are two different types of sensing devices, and the hot box detector will detect is a wayside detection system that is spread out every 25 miles or so, at least here in the U.S. on the Class 1 tracks. And they monitor the temperature bearing or the temperature of the bearing system as the train is going over. But on that note, RotoSense is able to do much more frequent measurements as opposed to every 25 miles. So you'll be able to see that temperature bearing kind of anytime you want to. Also, with the wheel impact load detectors, that's another wayside detection system, which is spread out even farther. And RotoSense combines both of those into the same thing because the wild systems kind of detect different types of flat spots in the wheel and also that unusual track interaction at that particular location. So again, the RotoSense combines both of those sensing capabilities into one sensor and makes it a very compelling business case for kind of our focus area. So the Sentinel Motion RotoSense Development Kit, or the RSDK like that we know it by, is something we deploy and offer to our customer base to just start interacting with this IoT sensing system and looking at different types of applications. We've deployed this in several different market areas, so obviously in the rail and transportation area. We're also in the energy sector in wind turbines, aviation, as some of the gearbox analysis that we were doing with NASA, and then also in industry and mining, conveyor systems and whatnot. We also work with a large number of universities for looking at different types of research. So this RSDK is a very flexible and easy way to start looking at different types of vibration analysis in these different areas. So the RSDK is comprised of one or more RotoSense units, the Sentinel Gateway and the Sentinel MotionView software application. And then another kind of unique application here that I thought I'd throw in is you can see here where there's different types of GPS locations, and this was using a RotoSense or an RSDK on a particular vehicle, and we were driving around near our office here in Tucson detecting potholes. And interesting enough, after we did that, the city sent out maintenance crews and started fixing some of these. So if anyone's been in Tucson, some of the potholes out here can get pretty bad, but you can see here the red ones are pretty severe, the blue are minor, and then the yellow are kind of intermediate according to the acceleration we were observing there. And here are some of the anomaly alerts that we send out when we detect these types of systems or abnormalities, and these are sent through either a text message or they're logged on the gateway or through an email. And you can see where this is very much applicable in both the railroad industry or even a helicopter gearbox system. So if you're detecting these types of anomalies and you want to alert the operator or the pilot or whoever it may be, this can be done quite easily through an API. So in summary, today we focus on this control and data flow framework as implemented in Sentinel Motion. We also talked quite a bit about this particular sensor framework by utilizing the RotoSense, the gateway, and the Sentinel MotionView software application. So in terms of a CDM and PHM system architecture, I think we tie everything together in this particular family member of Sentinel Suite. And we also covered some of that RotoSense development history, also the ongoing research and vibration analysis, and the railroad application areas that Ridgetop is utilizing Sentinel Motion in. So it does look like we're finishing kind of on time, and now we have some good time for questions. So let's go ahead and open that up. Yeah, so I am checking the chat feature here, see if there's any questions that may be coming in. So yeah, if there's
Hi, Alex here.
Oh, okay. Here you go.
Hey, how are you doing?
Good. How about you?
I'm fine, thanks. I have a doubt about the railroad sensing. what are the measurements that you can do, and how many sensors you need to install it for track maintenance purposes? Will you put it on the local or the rail cars or both, or how do you combine that, or more than one sensors?
Yeah, great. That's a great question. I have another kind of presentation that would cover that entire deployment scenario, but basically we have sensing capability of up to 200 Gs, and the sensor can be mounted on either that bearing system or the actual bogie itself, so typical or different mounting locations give different measurement requirements, but our target application area is on that bearing system, and we've seen a lot of good data results there. And again, by doing that, we're able to monitor the bearing, and the sensors can be communicating to the gateway in either a star network or a mesh network. If they're in a mesh network, you can kind of have the sensors spaced out down the length of the train on different vehicles, and you would issue kind of a sequential data collect, and all of those sensor measurements would be translated across each sensor back to the gateway. You can have up to 254 sensors on a given subnet, but they can't all be communicating simultaneously. But depending on how the data collection is scheduled, you can definitely monitor a large number of vehicles.
Okay, and how many in the same train? I have two in the bogies, front axle bogie, and then I have some in the rail cars. And how far can these sensors be from the receiving?
So they will need to
sensor?
be within 30 feet of each other or the gateway.
From each other, so they act like a chain.
Yes.
Okay, this is good because you can basically check the whole train.
Yep.
Okay. Thank you very much.
Okay. Yeah, great question.
Thank you.
Anybody else have any other questions at this time?
Yeah, hello.
Hello.
Yes, so I particularly joined hoping to hear about a few sensors that are used within the oil industry that I'm in, and to see. But I mean, I didn't see too much of that. But it's something that you don't have so much sensors used within the oil industry, like offshore.
Can you repeat that last part?
Oh yes, so I said, do you have sensors that you use for whatever kind of monitoring offshore platforms, the rig?
Oh yes, so yeah, the particular sensor in the RotoSense module is kind of flexible. So as you can see in the different form factors, we've utilized different types of accelerometers, different types of temperature sensors. It can all kind of be customized for different applications, and that's something we've done with various customers in different application areas.
Oh, okay.
Okay, so any other questions? Sam? And again, if anybody has any questions after the webinar and you get to review the slides, and if you have any questions, definitely feel free to send me an email or even Motion, and we'll get back to you in a very timely manner. So, but yeah, I think we'll give it a couple more minutes here, and if there's any questions, we'll keep answering them. All right. So yeah, as another reminder, our upcoming webinar schedule is here below. Our next one in this PHM series will be on August 12th, same time on Sentinel Power, and this time we'll be looking at the Sentinel Suite component and how it's utilized to monitor different types of power systems. And then on September 9th, we'll look at Sentinel Interconnect, which again looks at different types of the quality of interconnects at both cable level, solder joint level, etc. And then in October, we'll do that Sentinel Network webinar as well. Another webinar that is not necessarily part of this PHM series, but we're targeting in August, is on a product we call SalSage, and that'll be covering a battery life simulation tool. So I'll be sending out an email to anybody that's interested in that, and that's another exciting product line that we have to offer at this time. All right, so yeah, again, if any questions do come up, feel free to reach out to us. But again, thank you everybody, and I'll be ending the meeting here shortly.